Assalamualaikum to our lecturer. We are group 9 and today we are going to present our project which is vertical farm aquaponic greenhouse. This project focus on developing an automated greenhouse system that integrates vertical farming and aquaponics using Arduino based monitoring and control. Before we begin, let me introduce our group members. So the first one, our group consists of Nasaruddin, me, Ali, Shawal and Aiman Zakwan. Without further ado, let's begin our presentation. For content for our presentation, we have introduction, Tinkercad simulation, Sudoku and flowchart, schematic diagram, I/O table, Tinkercad circuit and sensor explanation, C++ code analysis and conclusion.
Let's start by introducing our project. As global demand for sustainable agriculture continues to rise, there's growing interest in integrated systems that combine vertical farming and aquaponics. Essentially, growing crops without soil by raising fish, all within a single closed-loop, water-saving ecosystem. For this project, we designed and simulated an automated control system for a vertical farm aquaponic greenhouse built around an Arduino Uno and simulated using Tinkercad circuit. The core idea behind the system is continuous self-regulation. We use the network of sensors to monitor several key environmental parameters such as air, water temperature, pH level, water level, light intensity and soil moisture.
So now I will be demonstrating our circuit system, how it works and how each component responds to each other. After start installation, C, the display is on and the power indicator is the green LED with an output. So this is the default, as you can see from the accelerometer, this is the default value. So I will choose the scenario which are stable conditions, climate with temperature change, and the last one is the emergency situation where the buzzer will turn off. So for the first scenario, so the first scenario is a stable condition. Where we set the stable condition is 80% water level, pH of 7 and temperature of 24. And water temperature of 7, that is 6%, and the sun is 7%. So now from the accelerometer, so we can see the other component is not reacting. Like since everything is in stable condition, the aquaponic farm and the filtration fan is not turned on. Unless the aquaponic farm, because we set it to be turned on for 5 seconds. If there is no discrepancies or crucial conditions, that will affect our system. And then it will turn off for 10 seconds. And if everything is stable, it will continue to sleep. So now let's move on to our second scenario, which are the climate change or temperature change. So what I mean by it is when I change the temperature, air temperature, which are above 50 degrees, the roof vent will be open and also the fan will be running to cool down the greenhouse. Then if we change the soil moisture below stable requirement, which are lesser than 30%. So you see the group of LED is turned on, which means the group of will pour down water to increase the moisture further. So that our system will go to system. And also we did this to avoid wasting water. So next is light. When we change, the light is below the standard requirement, which are lesser than 40%. Then the light grow lights will be turned on, which indicates by this white light will be switching to night time. And that's what it is. For the emergency situation, I'll demonstrate if there is only two secure conditions. It will mix the emergency alarm to trip, which the first one is when the water level sensor is below than 20%. Now you hear there is the sound alarm on this buzzer, and this will be also turned on simultaneously with the buzzer. And I will take to the level stable condition 8 and see for the second condition. So the pH level is less than 6 on both. divider and the LED on surface. And I'm going back to the statement function again. Okay, so lastly is the temperature water of the temperature water. This is about 28. It will be triggering the alarm as well. Okay, that's it for second action.
This is the flowchart of our project from our report. First, as you can see, we connect the sensor with the designated pin. After that, we set the condition in the coding, for example, pH water, water level, and each other. The details of the condition and the sensor will be explained in the simulation parts with the project itself as a proof of a functioning project. And this is the pseudocode for our project. This is derived from the flowchart to make the coding part become easier. Here it shows our coding project briefly in output, input, and also the loop.
This schematic diagram shows the complete automation system for our vertical farm aquaponic greenhouse. It is divided into two sheets. On sheet 1, the Arduino acts as the main controller. It receives input from the ambient light sensor, temperature sensor, soil moisture sensor, and water level sensor. Based on this reading, the Arduino controls the servo motor, updates the 16x2 LCD display, and activates the green and white indicator LEDs to show the system status. On sheet 2, the Arduino controls the output devices including the aquaponic water pump, ventilation fan, emergency buzzer, and red and yellow indicator LEDs. The NPN transistors are used to safely switch the pump and fan since they require more current than the Arduino can provide. Overall, the Arduino continuously monitors all sensor data and automatically controls the greenhouse environment, ensuring optimal condition for both plant growth and fish health while minimizing manual intervention.
For the input-output table, we have 6 inputs here, which is all the sensors, which I can explain in the next slide. And we also have the output, which is automated roof fan to cover the plants when it is normal temperature. We also have drip irrigation, emergency alarm lines, ventilation motor, fan motor, aquaponic pump motor to circulate the fish water on a 5-second on, artificial grow lights when the sunlight is low, and system power indicator, and also a feedback system for LCD status screen. Okay, so for the Tinkercad circuit, we have microcontroller and hardware setup, which is Arduino Uno as our core controller that manages 6 analog inputs and also 6 digital outputs. We also have user interface, which is 60x2 LCD display and serial telemetry log at 9600 baud. Okay, for the sensor, we have the MP36 sensor to monitor air temperature and also water temperature, the potentiometer for water pH level and water level, and photoresistor LDR to measure sunlight level, and also soil moisture sensor to map the percentage of vertical growth of bed hydration. Next, for the circuit loops, we have automated sensor actuator loops, which is we have climate control, which is when the air temperature is more than 30 degrees, it will activate the DC fans and also rotates the server roof vent. And when the ambient light, which is sunlight, less than 40%, it will turns on the white LED grow light. And when the soil moisture is below than 30%, it will open the drip solenoid valve. And second thing is emergency safety overrides, which is when it meets the trigger condition, it will automate the safety action, which is it will fire the red LED and buzzer simultaneously, and it will force disable water pump to prevent water damage. And also the LCD screen will alert the user with alert triggered, and also saying the hazards that will happen.
For C++ code analysis, we have 4 major components. One of them is loop. Inside the loop, we have read or sensor, where it reads 6 analog sensor and convert it into a read unit. Then we have 3 control functions, where it controls the climate, light and irrigation. After that, we have update feedback, which is updating the status to the LCD and serial telemetry. Then, we have evaluate safety, where it check the water level, pH value and temperature limit. After that, we have the safety first decision logic. It have a condition where water level is below 20%, or the pH value is outside 6 or 7.5, or the water temperature is outside 18 or 28 Celsius. But when the condition is reached, it will trigger an override system. The next one is sensor and input unit conversion, but already been explained from my teammate previously. So for the non-blocking timing with millis, this one is comparing the current millis to previous pump millis. Once the interval fast, it will toggle the pump state to the update into the pin output. So why does it matter? Because to ensure no frozen sensor during the pump cycle. And the next one is time duty cycle, where the pump run for 5 seconds and it will off for 10 seconds. This to protect the motor and avoid the overwatering the grow bed. That's all from me.
To conclude, our project successfully demonstrated the feasibility of developing a smart vertical farm aquaponic greenhouse using Arduino Uno and Tinkercad. By integrating 6 sensors and multiple actuators, the system was able to monitor environmental conditions in real time and automatically control irrigation, lighting, temperature and safety features. Overall, this project achieved its objectives by providing an efficient and sustainable greenhouse monitoring system. It also gave us valuable hands-on experience in programming, circuit design, sensor integration and embedded system development, while highlighting the importance of automation in modern agriculture. That's all from us. Thank you very much.